Now we're going to consider the forces that go into circular motion, specifically uniform circular motion. So we've discussed before that if I have an object moving around in a circle, so it's going around this way, the object, as it's traveling around, experiences an acceleration that points toward the center of the circle. So at each of these points, we have some velocity vectors that are tangent to the circle. But the acceleration vector is going to point in towards the center of the circle. And we call that a centripetal acceleration. And it took a value of v squared divided by the radius of the circle. Actually, I'll use little r for the radius of the circle. Well, if an object is accelerating, there must be some force on it, because by Newton's laws, the force is equal to the mass times the acceleration. The net force is equal to the mass times the acceleration. So if there is some acceleration, which there must be because our velocity vector is changing, there must also be a force. And we call that force the centripetal force. And we know that if I sum up all of the forces on an object, I must get the mass times the acceleration. Since this is moving in a circle, we know that this has to be the centripetal acceleration. Therefore, the centripetal force has to be equal to the mass times v squared divided by r, since the centripetal acceleration is equal to v squared times r. Now I'd like to make a quick point about this centripetal acceleration. There are many different types of forces that can cause a centripetal acceleration. Okay, so if we look at the moon traveling in a circle around the Earth as it goes around in orbit, the force that causes the centripetal acceleration is just the gravitational force. If I look at the motion of a windmill arm going around, if you go through Iowa, you see any of those big wind towers that give us electricity. The force causing the arms of the windmill to go around is some combination of the wind and the internal forces due to the stress and strain inside the arms of the windmill. Okay. So there's a lot of different types of forces that could cause you to undergo circular motion. In fact, you could have a large combination of forces that work together to give you a net force, which gives you a centripetal force. But whenever we have an object undergoing circular motion, we call the net force the centripetal force, and that is always going to be mv squared over r. So this is not a type of force. It's what we call the force, the collection of forces, possibly, when they conspire to give you motion that is uniform circular motion. There's a fun little demonstration you can do involving centripetal forces. So I have here just a regular old glass of water. You can see that in there. And I'm going to spin this glass of water in a circle, and we'll see what happens. So I'm just going to take it, and I'm going to go like this. And you can see I didn't lose any of the water. Right? I didn't get wet. Just taking it, moving it in a circle. You can see all the water is still in there. So why is it that when I spin the water in a circle, and I'm spinning it around, and it's upside down when it's above my head, why is it that when I spin it in a circle like this, none of the water comes out? To figure out why the water does not come out of the cup, I want to talk about something called angular velocity. So I have here a bike wheel, and taped to the bike wheel are these red and green dots. So if I just spin my bike wheel around, you can see those red and green dots are going around. And since they're just taped to the bike wheel, they're going around the same angle in the same time. So when the red dot has traveled 360 degrees, the green dot has also traveled 360 degrees. However, the green dot, as you can see here, is actually going significantly faster than the red dot is. And the reason for that is the green dot has to go around a greater distance than the red dot does. The red dot's making a tiny circle in the same time that the green dot is going around in a big full circle. So we want to describe two things. We want to be able to relate the velocity or the speed of the dots to how fast their angle is changing. So we're going to do that by defining a quantity called the angular velocity. So first I want to figure out, well, how much has my angle changed? Well, let's say initially we were right here. Say our red dot was right there. It was at an angle theta I for the initial angle. And then we've gone a little bit of an extra angle. We've gone from our initial angle to here. We've just rotated a little bit further to be at some new final angle, which we'll call theta f for the final angle. And the change in the angle is just the final minus the initial. Notice that this is the exact thing as the displacement that we talked about for position. So for that reason, we call this the angular displacement. All we're doing is looking at the difference between the initial angle and the final angle. But that doesn't tell us how fast the angle changed. To do that, we need to define another quantity, which we're going to call the angular velocity. And the angular velocity is defined in a very similar way to the normal velocity that we deal with, just the regular linear velocity. The angular velocity is going to be the change in the angle, or the angular displacement, divided by the change in the time. It's a definition, so I'll give it an extra equal sign in there. Now notice, this is the exact same definition that we had for regular old velocity. This is just regular old velocity being defined to be the displacement over the change in time. Here, we're defining it to be the angular displacement divided by the change in time. Now, I'd like to be able to relate my angular velocity to the regular linear velocity describing how fast the object is moving as it travels around in a circle. And we can see, recall that as an object is moving around in a circle, its velocity is tangent to that circle. So I'm just going to draw a velocity vector like that. Now, there's a few things we can pay attention to here. Recall that the circumference of the circle, I'll write it down here, is 2 pi times the radius of the circle, which means that in the time it takes to go one full period around the circle, you've traveled a distance 2 pi r. Well, from that, we can figure out that the relationship between the angle that we travel divided by the change in time is just going to be the same as the velocity divided by r. Why is it the same as the velocity divided by r? Well, the angular velocity, let's say we consider a change in angle for one period. That would mean that omega was equal to 2 pi r, was equal to 2 pi divided by the period t. So the t would be the time it takes to go around the circle. But that's the same thing as 2 pi r over t divided by r. But the 2 pi r is just the distance you've traveled. So that's like a delta x divided by t. So delta x divided by t, that whole thing is just like your velocity. So I'm going to put a big box around this because this gives us two things. One, it gives us the definition for the angular velocity. That's just the change in angle divided by the change in time. And second, it relates the regular linear velocity and the radius to the angular velocity. Both of these things are going to be incredibly useful as we describe objects that are rotating or moving in uniform circular motion. Now let's see why the water didn't fall out and splash me on the head. Well, let's say here's me. Here's me. And I'm spinning the cup of water around. Let's say the cup of water maybe has some velocity, has some radius r. Now, as I was spinning it around, I was spinning it around at a rate about like this, which might mean that it's going around about 1.5 revolutions per second. Each revolution has 2 pi radians of angle in it, or 360 degrees equivalently, which would mean 1.5 revolutions, so going around once and a half, would be about 10 radians. So I said I was rotating about 10 radians every second. And the mass was, I said, about 1/2 kilogram. And I'm just throwing out rough numbers here. The radius, I said, was about 3/4 of a meter, so about 75 centimeters. So I want to know two things, one of which is how fast was the cup moving around? And then also, what was the centripetal force on the cup? So if we can do that. To figure out how fast it was moving around, all I have to do is go back to my equation for the angular velocity, which said that omega was v divided by the radius, which is the same thing as saying that v equals the angular velocity times the radius, which if I plug in my angular velocity of 10 radians per second, and my radius of 0.75 meters, would give me a speed of about 7.5 meters per second. Decent speed. We can also look at what our net force is, which is equivalent to the centripetal force. So the net force must be making the object move in a circle, so that's the same thing as the centripetal force. But as we said before, the centripetal force is going to be mv squared divided by the radius. So again, if I plug numbers in, I know what my v is. That was 7.5 meters per second. My mass, I said, was about 1/2 kilogram. The radius was 0.75 meters. Plugging those numbers in, you should get about 38 newtons of net force on the object, on the glass of water, making it travel in a circle. If we want to figure out why the water does not come out of the cup, it's helpful to do a free body diagram. So we just showed that the centripetal force, the net force on the object, so if I add up all of the forces, I get a net force of about 38 newtons. What forces cause that centripetal force? Well, one thing is pretty obvious, the force of gravity. The force of gravity is going to be the mass times g. G is about 10, the mass we said was 1/2 kilogram, so this will be about 5 newtons. Well, I still need a total of 38 newtons, so I need another 33 newtons to come in here from somewhere. Well, what's the only other object, or what's the only other force pushing on the water? Now when I say the water, I mean the water explicitly, I don't mean the cup. Well, it's not me, my fingers were gripping the cup, so I couldn't be pulling on the water per se. So it's got to be the force of the cup pushing down on the water, and we can treat that just like a normal force, because it is a normal force. So we'll say that this is a normal force, and in order to get a total force of 38 newtons pointing down, this normal force has got to be about 33 newtons in magnitude. What would happen if I did not have that normal force? If I didn't have the normal force, I would not have a big enough force pulling down on it to make it curve in a circle that had that radius. So the water would go flying out the top of the glass. So as I do this, as I take my water and I spin it around, the water would have come flying out the top. Now, the reason it doesn't fall out is partly because I have that normal force. Without that back, I don't have a normal force. The water comes flying out of the top. However, it could come flying out of the bottom if I moved too slowly. So recall that that centripetal force was equal to m times v squared divided by r. But that's got to be equal to the gravitational force plus the normal force. If I spin the object more slowly, something's got to change. If I make this side of the equation go down, so my centripetal force is smaller because I'm not spinning the cup as fast, well, the force of gravity is not going to change because the mass of the water certainly isn't going to change. But if I spin more slowly, that normal force gets smaller. So n is going to decrease. The gravitational force stays exactly the same. Now there's going to be a cutoff point where if I'm going slow enough, if v is small enough, eventually the normal force is going to become 0. So if I do this slow enough, the normal force will become 0. You can see it starts to, the water is going to start to come out there. You can hear it splashing on the side over there. I'm going to try to do it so that I don't get wet myself. But this is why I don't get wet, is because the water really wants to come flying out of the top of the cup. Because by Newton's first law, objects in motion, like the water, want to keep moving in a straight line. And I'm forcing that water to curve. So it's going to take a force to curve that water. And most of that force is going to be from the normal force if I'm going really, really fast. If I slow down enough, all of a sudden gravity becomes bigger than the normal force. And if I slow down even more than that, there is no more normal force. There's nothing pushing down on the water from the cup. There's no force from the cup pushing down on the water. So the water, we're moving so slow that gravity is going to be strong enough to pull the water right out of the cup. And what I can do, if I just take this glass of water, if I spin this fast enough, the water should not come out, which it just did. We're going to try that one more time.